Hello everyone, welcome to the control system. This is part 4 of lecture 8 on stability analysis for linear system. In this section we'll discuss the special case 1. So there are two special cases, but we're gonna discuss the first one here. So the special case is when the first column term element in any row is 0. So if the first column term element in any row is 0, but the remaining term are not 0, or there is no remaining term, then we need to replace the first 0 with a very small number, epsilons. So you need to replace that 0 with a small number called epsilons. Well, you can assume that it assume a positive number or negative number. That's fine. And then you need to continue the calculation as normals. So some element that follow will be the function of epsilon, of course. And then complete the array, then count the sign change in the first column as usual. So in this case, you allow epsilon to be very tiny numbers, almost 0, and the number of sign changes is equal to the number of root on the right hand side. Okay, and let's consider the example. So consider the following equation. This is the denominator of the polynomial, not the denominator, the polynomials of the denominators. And then you need to form the array of the coefficient. This is as you did before, but in this case you will find that there's 0 here, and this is not 0. So in this case, you need to allow this 0 to be epsilon. Very small number. It can be positive or negative. You can assume it later. And then after replace this 0 by epsilon, you can continue the calculation. Okay. For example, in this case, the result is minus 12 over epsilon plus 4. So epsilon is very, very small. Okay? So in this case, you can ignore this 4 because this epsilon will be very small. Not will be, epsilon have already assumed to be very small. So you can ignore this 4 and then continue the calculations. So until this point, this term is very small. You can ignore this one. It's only 6 remain and then continue the calculations. And after that, you can assume, we already assume it, but you need to pick epsilon to be positive or negative. So in this case, I just pick epsilon to be positive, and then check the sign change. There are two sign changes. Okay. So it is unstable. So because this is minus. Okay. Positive, negative, negative, positive. In this case, it is unstable system. In the special case 2, it is when the coefficient in any derived row are 0. So in that case, it indicates that there are two real roots with equal magnitude and opposite sign, and or two conjugate imaginary roots. So the evaluation of the rest of the array can be continued by first you need to form an auxiliary polynomials, and some people call it even polynomials. They are the same. Okay, you need to form this auxiliary polynomial with the coefficient of the last row, and by using the coefficient of the derivative of this polynomial in the next row. And such root with equal magnitude and lying radially opposite in S-plane can be found by solving the auxiliary polynomial, which is always even. And for the 2n degree auxiliary polynomial, their n pair equal an opposite root. So let's consider the following equations, very simple equations. This is the polynomial of the denominators of the closed loop transfer functions. If you do the array of the coefficient, you form the root array of the coefficient, you will obtain this table here, and you will end up having 0 here. So the auxiliary polynomial is this one, the upper one, with the coefficient 1 s squared plus 2 here is s0. And then you need to do the derivative. But first, this is actually the factor of this whole thing. So if you do the factorization, you will see that this s cubed plus s squared plus 2s is equal to s plus 1 times s squared plus 2. So the auxiliary polynomial is a factor of this one. Okay, this is auxiliary polynomials, s squared plus 2, and then you do the derivative, you will have 2s. So you just need to put this 2s here. This is 2 coefficients. And there is no sign change here, so the system is stable.